Hello and welcome to my channel, Ready to Derive, in our continued study of related rates as it pertains to rates of change of area. As a little background, I do have an introductory video, which I'll link below, introduction to related rates, and a follow-up video in which we explore changing distance and length. In both videos, well, in the introduction, I do introduce a four-step process for tackling these type of problems, so you can go back and check that out. But I will briefly review it in this video before we embark on actual practice problems. So without further ado, let's begin. So I'm going to briefly lay out the four-step strategy for solving related rates problems. If you want a little more detail or a little more depth, don't forget to check out the introductory video to related rates. So first step is draw a diagram and assign a variable to each quantity that varies with time. And label those variables into the diagram. It will be very helpful for step 3. Step 2 is for each variable. This is more of an organizational step where you take all the information from the question and you kind of just itemize what rates of change have I got, what do I want to find, and what I call snapshot values. That's the variables that we're talking about. Often they say at a particular moment in time, when the variables have specific numbers, what is the rate of change? So I call that rates of change, snapshot values abbreviated. Step 3 is to write an equation linking all the variables and then implicitly differentiate both sides with respect to time. That equation is easiest to write if you have your diagram from number 1 labeled with variables, not with actual specific snapshot values. That's the equation differentiate stage. And then step 4 is to substitute the values from step 2 that you itemize in step 2 into the equation and solve for the unknown rate. It's possible that you may have to find additional snapshot values that were unknown in step 2, but you can wait on that to see if that's necessary to the very end. And so that step is substitute solve. So for our first practice problem, we are looking at an equilateral triangle, which is growing. Sides increasing at 10 millimeters per second, and we'd like to know how fast the area of that triangle is increasing at a particular moment when its side is 20 millimeters long. So the first thing is diagram and variables. So here is our equilateral triangle, and we know that the side is one variable, that the length of the side is changing. So let's just call that x here. And we are interested in how the area is changing. Now, this is kind of hard to show in the diagram. I mean, I'll let the variable a represent the area, but it's kind of hard to show that particular variable. And we're probably going to erase that in a moment because we'll have to do more things with that figure. So the next step is the rates of change and snapshot values, just kind of like itemizing everything we're given, everything we have to find. So we're told that dx by dt equals, let's see, 10. And we're interested, so the snapshot value is when x equals 20. And we would like to find dA by dt. And at that moment, we're not given the area at the moment, but we could find it out if we needed to, but we'll hold off on that because we may not need it. Okay, so the next step is to write the equation relating the variables, that's a and x, and differentiate. So we know that the area of a triangle is half base times height. And we can see here that the base is, let's see, the base is x, right? That's the variable there. And we just have to figure out the height. So let me remove that for a moment. And let's go in and maybe use green for the height. So we need to, now we could use a variable h for this, but then that would be introducing another variable, and we're not even given the rate at which that height is changing. So we probably can express it in terms of x. Now recall with an equilateral triangle that the angles are all 60 degrees. That means that, and that this one at the top, at the vertex, is split into two angles of 30. And if you recall that when we have a, let's see, a triangle, look at this right triangle here. It's a 30, 60, 90 triangle. It's a very special triangle. And x is the hypotenuse opposite the right angle. And if you recall, the leg that's opposite the smallest angle, the 30-degree angle, is going to be half of that quantity. So this here, so if the length is x, the hypotenuse, this leg here will be x over 2, and the height will be radical 3 times x over 2. So let's put that. That is the height, radical 3x over 2. And let's sort of condense that a little. So we have root 3 over 4 times x squared. And that's what our a is in terms of x. So we've related the two variables, and now we can differentiate with respect to time. And when we do that, we get dA by dt equals, rad 3 over 4 is a constant, so we can put that aside for a moment and take the derivative of x squared, which of course is 2x. But because it's the derivative with respect to time, we mustn't forget implicit differentiation to multiply by dx by dt. And the final step is to substitute and solve. Before we do that, maybe we should tidy it up a little bit. So the 2 cancels with the 4, leaving 2 there, x dx by dt. And now we can substitute. So x, the particular value of x is 20, and dx by dt at that moment is, at the moment we're considering, is also 10. And if we work that all out, we get 200 over 2 is 100 rad 3. And the units, because its rate of change of area would be millimeters squared per second. So here is the rate at which the area is changing, so dA by dt at that particular snapshot moment. So for our second practice problem, we have a snowball whose surface area is decreasing at a rate of 1 centimeter squared per minute. At the moment, its radius is 4 centimeters, and we'd like to know how fast the radius is decreasing at that moment also. So diagram and variables once again. So it's a little hard to show sort of this information, but if we kind of take this circle and make it look somewhat like a sphere, we know this is one variable of interest is the radius. And of course, if we could shade the whole surface, the surface area, let's give that a variable. Let's call it S this time. All right, so let's identify what we're given and what we need to find. So ds by dt, the rate at which the area is changing, is going to be negative 1 centimeter squared per minute because it's decreasing. The surface area at that moment, we don't know, but we could find out if we need it. We would like to find dr by dt, and we know at that moment the snapshot value of the radius is 4 centimeters. So now we write the equation, differentiate it. So you kind of have to just know this formula. It's the surface area of a sphere is 4 pi r squared. And if we differentiate both sides with respect to time, we get ds by dt equals 8 pi r, don't forget, times dr by dt. And the last step is to substitute and solve. So ds by dt is negative 1. 8 times pi, the radius at that moment is 4, and we'd like to find dr by dt. So if we divide through, we would get negative 1 over 8 times 4 is 32 pi. And if we just want to sort of understand that as a number, work it out, and it comes to about negative 0.01. And of course, the units of that, because its radius, is centimeters per minute. So that is the rate, dr by dt, at which the radius is changing at that moment. So for our last practice problem, we have a rectangle inscribed in an ellipse as shown. And what's going to happen is the vertex or vertices of that rectangle are going to move in such a way that it stays inscribed in the ellipse. So let's imagine we could have different shapes and sizes depending on where the vertices are. And we're just going to focus in on one location. When the upper right vertex of the rectangle is 3, 1, its x-coordinate is changing at a rate of 1 unit per second. At what rate is the area of the rectangle changing at that moment? So let's have a look. So we have, let's just get the one, there we go. That upper right coordinate is at 3, 1, and we'd like to know how fast the area is changing. So we sort of have our diagram and the variables set up already. well, actually, we need to set up the variables. What we need to do is to think about what determines the area. Well, it's the width and length of the rectangle. And what important information do we have? Let's see, we have that, we have this distance here would be the x coordinate of that point, and this here would be the y coordinate. And then, of course, we're interested in the area of that rectangle. We'll call that A. So we have X, Y, and A. So we have to identify the rates of change we're given and the snapshot values. So we know that dx by dt is changing at 1 unit per second. We didn't know in which direction. Let's just assume it's moving to the right. And at that moment, x is 3. And y will obviously be changing as well if it has to stay inscribed in the ellipse. We don't know that rate, but we do know y equals 1 at that moment. And we are interested in dA by dt. And now the area, that's actually pretty easy to figure out at that snapshot value. So let's get it just in case. So we have here, we know that this length here would be 3 times 2, which is 6, and this will be 2 times 1, which is 2. So we can say that this is 6 and 2, and the area will be 12. Now we have a little issue here because we want to find dA by dt, but we have another rate that's unknown. And that's going to be impossible to do unless we can find a way of calculating the snapshot value of dy by dt. And we can because we have the equation of the ellipse. So this is a little bit more of an involved problem. So to get dy by dt, otherwise we have no chance of getting dA by dt, let's take the equation of the ellipse and let's take the derivative with respect to time of both sides. We get 2x dx by dt plus 4y dy by dt, and the derivative of 11 is 0. And if we maybe before we plug in, we'll just rearrange that. So dy by dt, if I bring this term to the other side, so negative 2x dx by dt, and then I just divide through by this coefficient 4y, I'll put that here over 4y, I have a way to relate dy by dt to dx by dt. So obviously, look, we have the 2 cancels with that 4, leaving 2. And we have that negative x, so negative 3 over 2y, y is 1, so that would be, so what, that's just right, 2 times 1. And dx by dt is 1. So we get that it is negative 3 over 2, or negative 1.5. So we can go in, that's kind of very helpful. So we can go right in there and put that, since that's one we just calculated, we'll put negative 1.5 here, and then we can proceed. Continuing with the problem of the rectangle inscribed in the ellipse, we are at step 3, which is to write the equation, linking the variables, and differentiate. All right, let's recall that the variables are, we have, because we're interested in this upper right coordinate here, we know that this is its x coordinate. Sorry, that's a bit messy. And this is its y coordinate here. So therefore, the area of the rectangle is length times width. Well, the length would be 2x and the width would be 2y. So the area equals 4 times x times y. Now we're going to take the derivative with respect to time. And we have to be careful here because x and y, we have to apply the product rule because we have both x and y are dependent on t. So dA by dt equals, we'll just keep that 4 factored out for a moment, that constant, and take the derivative of x times y with respect to t. So by the product rule, dx by dt times y plus x times dy by dt. And the next step is to substitute and solve. So it would be useful to call up the table of values that we got before, and we get dA by dt equals 4 times 1, right? That's dx by dt, and y, the snapshot value of y is 1, plus the snapshot value of x is 3, and dy by dt we figured out was negative 1.5. Notice that we don't actually have to use the snapshot value after all, but it was worth finding it just in case. And then we have 4 times, let's see, 1 minus 4.5, and that comes out to negative 14 units squared, because it's the rate of change of area per second. So that's our final answer. And notice it's negative, which means it's decreasing. So why is that? Well, if you think about, so the x-coordinate is increasing at 1 unit per second, but the y value is decreasing by negative 1.5, so a little faster. So I guess the overall effect is that the area of the rectangle is shrinking at the rate of 14 units squared per second. Thank you for sticking around to the very end of the video. If you enjoyed it, found it useful, please do like the video and subscribe to my channel, Ready to Derive, and check out some of my other videos.